uh, I'm beginning to think maybe I've started at too rapid a pace, and a certain maybe I should have made the following things clear. See, in finite dimensions, when you have a normal operator, you know that you can diagonalize it. You can find a orthonormal basis of eigenvectors. So the good way to study a normal operator is to think of it as a diagonal matrix, and then you can talk about functions of that thing being just those functions of those diagonal values. Now, the whole reason for this entire fuss that we've been doing about the spectral theorem in infinite dimensions is that in infinite dimensions you may not have eigenvalues. That in general, the classical example is to look at L2 of let me just say L2 mu. You have some space, you have some measure. On L2 x mu, and suppose you look at and let's assume that x is a subset of the complex plane, and you look at the operator given by Lz c of x of z, sorry, equal to zc of z for all z in x. They like saying in finite dimensions, I want to say you have a matrix lambda. I use this z. Okay, let me just call this. Look at L psi of z equals z psi of z. This is the analog of saying in finite dimensions you look at d psi of y equal to lambda I psi I. The index set is here is a finite index set, here it is a continuously varying index set. Right? And the point is that in this example, I think I may have given this as a problem for you, that mu is an eigenvector, an eigenvalue of L precisely when, so what does that mean? That means z psi of z should be mu psi of z for almost every z in x, right? So this means there exists non-zero psi in L2 such that L psi, what is L psi of z? It is z psi of z equals mu psi of z. There are too many mu's, there equals alpha. For mu almost all z. psi of z, that is what L psi of z is. We are saying that L psi equal to alpha times psi. That means that these two functions must agree mu almost everywhere. But what does this equation say? This says that if psi c is not identically 0, so the set where psi is non-zero has positive measure. And if psi of z is not 0, see, this implies that if psi of z non-zero implies z equals alpha. Mu almost everywhere. So what does that mean? That means, what does this mean? This means that the set where the psi can only be supported on the point alpha. Like here, something can be an eigenvector precisely when it has non-zero coordinates only at those i's for which lambda I is mu. Everything else should be 0. So this means mu of the set where z not equal to alpha. See, z not equal to alpha means psi equals 0. So this set is contained in the set where psi equals 0. But that is not everything. So I'm saying times z equals alpha. Is not 0. I'm saying this clumsily. See what this says, that the set where psi is not 0 is just the singleton alpha. And psi is not the 0 element of L2. That means the set where psi is not 0 must have positive mu measure. That means the point singleton alpha must have positive measure. That means in this example, this operator L can have eigenvalues only if there are singletons which have positive mass. That is, this measure must have atoms. There will be points which have positive mass. So if you take a measure which is non-atomic, like Lebesgue measure, Lebesgue measure gives 0 measure to all points. In such examples, these multiplication operators will have no eigenvalues. So you can't deal with them as you do with eigenvalues. So that is why you look at things, you develop this functional calculus to work with them. And in the case of one-dimensional algebras, it is convenient because you can talk about the set where for any the spectral projection for x corresponding to the set E. So in this example, if E is a subset of the complex plane, once a B of X will be just multiplication by the indicator of E. Once a B of L will be just multiplication by the indicator function of E. So the whole thing of the continuous measurable functional calculus and so on is because we don't generally have eigenvalues. If things were diagonalizable, like in the finite dimensional case, then we don't have to do all this. Okay, so let me complete the thing I was trying to do last time. We were trying to prove this theorem. If E is a projection in M. So if you take this coordinate of M determined by E, so I will call this the coordinate of M determined by E, because if you think of represent operators as matrices, block matrices, with respect to range E direction of current of E, so that E looks like 1, 0, 0, 0, then for an X in M, the XE this ME will be all those there exists X which looks like XE something 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 in M. Right? This is exactly what ME is. The cut down of, so we think of this as cutting down M by E. So this is why we call this the coordinate of M determined by E. The 1, 1 coordinate of the matrix is what we're looking at. And so, and this statement says if see M prime will look like diagonal matrices, because E is in M, E is 1, 0, 0, 0, and if that commutes with the matrix X prime, then X prime must have non-diagonality 0. X prime must be diagonal. Okay. So we were trying to prove this, and the way we tried to do one inclusion was clear, right? Everything here will clearly commute with everything here. And this was clear. They just say, because we take an X prime and M prime, X prime E, X prime looks like let me use the same notation. X prime will look like X prime E, X prime E perp. X prime must look like this. And so, because it's in the commutant, this will commute with anything in M. So, to say this commutes with this will mean, by that thing where I asked you to do this exercise of multiplying things by diagonal matrices, it shows you that this X prime E must commute with XE for every XE. Right? So, that is the proof that this inclusion holds. And for the converse direction, what we had to do was to show that given something in the commutant of ME, we wanted to show that in fact you can find if it if I take an A prime in the combinant of ME, right, that means A prime sits is something that lives in the top corner. It's a mapping from the range of E into the range of E. Right? So what we're asking is there exists X prime and M prime such that X prime E equal to A prime. That's what we're trying to say. So just from the fact that this is in E, we wanted first so the way we tried to prove this was to say we did it in two stages. So we first concentrated on unitaries. We took a U prime, which is a unitary in ME prime. And then what we showed was that there exists a unique, I call it U naught prime, I think. There exists a unique U prime in fact, M prime cut down by the central support of this projection. Unitary such that U prime E equals U naught prime. So this is what we proved last time by going through that, using that KRP lemma judiciously. And we went through the argument as well, let me not repeat the thing. So we showed that, see what does this say? See, E is below the central support of E, right? So I can, see, for example, suppose I call E1 as E, E2 is ZE minus E, and E3 is 1 minus ZE. Right? E is the projection, it is sitting inside Z of E. This means that these are three projections which are orthogonal and they add up to 1. Is that clear or not? And what we've said is that if you take a U0 prime in U of ME prime, that means you start with the u0 prime, which lives in the 1 1 corner. So I write things with as a, what is the reason for introducing E1, E2, E3? That I want to write elements of, I want to decompose H as direct sum range EI. And I'm increasing projections. E1 is the smallest. The central support of E is larger than that. So the central support of E is just E1 plus E2. And E1 is P. E is E1. And in this, if you write things as 3 by 3 matrices, E will look like this diagonal matrix. The central support of E will look like 1, 1, 0. And what we said is that if you take a u0 prime which lives on the range of E, and it is a unitary in ME prime means when one writes this, ME by definition is an algebra of operators on the range of E. So its commutant lives only on that range of E. So u0 prime lives in just this corner. So what this thing says is that you can find a u prime which has u0 prime in this spot, and maybe you call the u1 prime. Let me call this, because let me call this E1. We started with U1 prime. Then you can find a U prime, because I took the E as E1 and that lives on E, I'll call that U1. So the U looks like U1 prime. It is unitary on this corner. U prime is unitary which lives on the first two pieces. And if you have a unitary operator on H direct sum K, which is already a unitary on H, then it must have 0 entries here. Because this is already norm-preserving. If there is anything non-zero here, the norm will be bigger than 1 somewhere. So, U prime has to look like this. So that's what we said. We started with the U prime which is in ME prime. And now I have extended uniquely to something which is slightly larger. It lives not just on the range of E, but on the range of the central support of E. U prime looks like this. It lives only on this piece. So now I can define a V prime as U1 prime, U2 prime, and I want some unitary operator on the third piece. So what is a unitary operator? Give me an example of a unitary operator on the third piece. The third piece is the range of 1 minus ZE. I want a unitary operator there, means you can always take the identity operator there. The identity operator on the range of E3. Then this thing will be unitary on the whole space. So what you have done would have come up with something see what they said, that U prime is something in the it's a unitary in M prime ZE. That means it must itself be a unitary in M prime, which lives on the range of ZE. So this fellow is in U prime. So U1 prime, U2 prime, the diagonal is in M prime. And so the whole thing is also an M prime. This is an M prime. And V prime cut down by E is exactly that U1 prime. You started with some U1 prime in unitary in ME prime, and you wanted to say that there's some unitary in M prime whose corner was at U1 prime. So here this is not unique because you had choice on what you did in the third spot. This unitary if you want to be in M prime, it must certainly commute with the center of M. That means it must commute with the center support of E. That means anything in M prime must look like something direction something, you have zeros here. Anything in M prime must look like this. And so we're just building this thing up slowly. You have this U1 prime, so they say that the unique way to build it up to the central support. And once you've got it up to the central support, then you can build it to the whole space by trivially extending on the remaining piece. The last bit of this chapter, he devotes to some things he called phases, and then I don't want to introduce these abstract things, and then he defines what he means by a phase, and then he characterizes these phases and so on. But rather than doing that, I want to write down the way in which this thing comes up naturally, where he would be actually using this. See, let's first go to the commutative case. If you look at L infinity of mu, of from sigma mu. So this you know purely as an algebra. I just give you this algebra L infinity. From that I want to capture mu. How do I think of mu as something related to this algebra? Or what is the Rees representation theorem say? If you take a continuous function on a compact Hausdorff space, then the positive functionals there those bounded functionals on this C-star algebra which are positive, they came from measures. So correspondingly what we'd like to do is to take the because I've started with the one-dimensional algebra, I might want to look at normal positive functions. The word normal, okay, I haven't introduced this word. Sigma weakly continuous. Positive functional on this. Will be, what will that be? What are the sigma weakly continuous functions on this? What is the pre-dual of this L infinity? There is just L1. So what is L infinity? What is the pre-dual of L infinity? What is some space whose... So then it is L1, right? Okay. And so if mu was finite, then you can think of mu itself as giving you an element of L1. Namely, it is a constant function. See, one way of thinking of L1 sigma mu is as all, you identify this with all measures which are finite measures which are absolutely continuous with respect to mu. Finite complex measures. Then their random equilibrium derivative will give you that L1 function. So you can think of L1 functions as such thing. So the positive things here are the positive measures, mu, nu, which are absolutely continuous with respect to mu. Right? So if I have a these are actually finite positive measure because it's L1. The nu must be a finite positive measure, only then that is what the integrability condition says. d nu by d mu is the density function which is integrable. That means that nu is a finite measure. So finite positive measures can be identified with sigma weakly continuous positive linear functionals on this algebra. So that is the analog of this, analog of finite positive measures. Absolutely continuous with respect to mu. The analog of this at the algebraic level, see, this is for a commutative von Neumann algebra at infinity. This corresponds to this m star plus. For a general von Neumann algebra, the analog of a finite positive measure will be given by an element of m lower star which is positive. What does it mean to say it is positive? When is a linear functional positive? If it takes positive values on positive elements. Right? This by definition is all rho in m lower star. So that rho of any x star x is positive. No, this is a commutative von Neumann algebra. So when we want to go to the non-commutative setup, so we want to get an abstract.
You are abstracting.
L infinity is the is really the only possible commutative von Neumann algebra. If you say you only want to look at von Neumann algebras whose pre-dual, the von Neumann algebras are things which have pre-duals. And the sigma finiteness thing that you pointed out earlier, the kind of the analogous restriction is if you see, or in any case, we want to only deal with separable Hilbert spaces. So these von Neumann algebras you must be able to realize on separable Hilbert space. And that will happen precisely when its pre-dual is actually separable. Okay, so I'm saying any commutative von Neumann algebra with separable pre-dual is identifiable with an infinity sigma mu. Actually, don't take that. There is almost correct. See, sigma finiteness and the separability are not quite the same, but I'm studying over those fine points. I only want, because I only want to deal with separable Hilbert space, because I want to talk about measurable functional calculus. And to deal with measurable functions, I generally want finite countable operations. So which is why I want to stick with separable hypothesis. So anyway, our interest will be in von Neumann algebras whose pre-dual is separable. Okay. So in some sense, these are any commutative von Neumann algebra with a separable pre-dual will look like an infinity sigma mu. Okay. So to cut a long story short, what I'm trying to get at is what happens if one even wants to relax this condition. I want to look at the analog of infinite measures in this context. So that has a name, so one calls so I want to think of it as something like this. Except it's not a linear function, it's not defined on everything. Because M lower star acts as functional, I mean everything in M acts as functional on M lower star. See, rho of 1 will be finite precisely when the measure is finite. See, so the objects you are looking at 1 they must give you value infinity. So we just define formally a weight one algebra is just a function. So you allow some things to take infinite values, and you want it to be additive, right? Such that phi of ax alpha x plus y is alpha phi x plus phi y. For alpha positive, xy positive. With the understanding that infinity plus anything is infinity. Infinity plus alpha is infinity. So such is a weight. So this is very abstract. So what does one do with this? So one would like to see, as in the finite case, one wants to, given us, in the finite case, if phi of 1 is finite, then this phi can be extended to actually a positive linear function. It's just like your usual integration theory. If you can integrate positive functions, then you can integrate all functions. So any self-adjoint is a difference of two positives, and if all elements have finite integral, so you're only talking about integrable functions. If phi of 1 is finite, the whole measure is finite kind of thing, then you can extend such a weight So I just take that as an exercise. Phi of one finite, if and only there exists a phi tilde in M star plus such that phi tilde associated to M plus is phi. So one way is clear. If there is a positive function on M, which and if you restrict it to M plus, that will give you a weight. It will give you a finite weight. Meaning it takes only finite values. I'm saying this implication is obvious. It should be. And conversely, if phi1 was finite, this is like you know how to integrate positive functions. And you want to extend the integration to all complex valued functions. So take any self-adjoint, you write it as a difference of two positives. Define the value of the integral as the difference of the values of the integrals. That is well defined because of this additivity. If x1 minus x2 equal to y1 minus y2, then x1 plus y2 will be x2 plus y1. So the phi values will add up, and then if you subtract, you will get phi x1 minus phi x2 will be equal to the corresponding thing for the y's. So that will give you a well-defined definition on all self-adjoints. Huh? Yeah.
Not plus.
Phi is a weight. I'm assuming that phi is a weight. That means it sends M plus to non-negative things.
Phi tilde will not act on plus. Like how if I know.
That is why I wrote phi tilde restricted to M plus is equal to phi.
In plus star phi tilde.
Sorry, no, M star plus is those things in M star which are positive. So the notation is those things of M star which send positive things to positive numbers. So that is by definition the positive cone of the dual space.
But in the integration theory, we integrate on at first positive, then not.
Suppose I know how to integrate all positive things. I have a finite weight. That means, and I know how to integrate these positive functions and get finite values. See, the differences will give you a problem if you allow infinities. That is why this works only if the integral takes only finite values or positive things. Then you can extend it to an integral on all real things. And then on complex by Cartesian decomposition. Exactly the same argument will show that if phi1 is finite and if phi is additive like this, then you can extend it to a linear function on the self-adjoint elements, a real linear functional on the surface charge of M, and then to a complex linear functional on the R of M. Right? You have to do a little bit of work to go from real scalars to complex scalars, but all that is something that you sit down and do it once and you realize that they can always work. Okay, so in general then, given a weight, I want to pretend like I have, so I would like to talk about, see, if phi was in M star plus, for this, any self-adjoint C star algebra is enough. I don't need a one-level algebra. I'm not talking about the one-level features as yet. So actually I could have defined this weight on a C star algebra, not just one-level algebra. Phi, a weight on a C star algebra the map from A plus to this, so that this is true. This A star plus. By the plus of A star, one means those things in A star which are positive on positives. So to this thing one can so I want to pretend like we're dealing with a measure. We have a measure, the thing, our one-level algebra looks like L infinity of the measure. The natural place it acts on is L2 of that measure. So I want to lay hands on L2. I want to get a Hilbert space from this, so a natural, so let me go back to, so I think it's good to stay with one-level algebras. Let me assume that M is a one-level algebra. And phi a weight on M. To this weight, I want to associate some things which will be naturally associated, which we'll naturally have to deal with. So let's define T phi. Think of this as the domain of phi. That is that place where phi is finite. So there's all those x in M plus, so there phi x finite. And I don't know why they use the notation always, an n phi like this. So this is all those x in M such that x star x is in phi of x star x finite. So pretend that you're talking about L infinity. M is L infinity, and that phi is given by an infinite measure on that, which is absolutely continuous with respect to that measure mu. Then this is all those positive functions which are integrable. This is L1 intersect L infinity. And this is L2 intersect L infinity. Okay. And so you would like the completion of this to be your L2. So you need to do a little work. So let me write anything here. This is N phi star N phi. By which you mean all things of the form and this is something like L1. If you multiply two L2 functions, you will get something in L1. So I mean, so let me prove the the reason one has to look at this sort of thing is, for example, when you look at when you're studying a group, the natural thing to do is look at its R measure. You want a translation invariant measure. Look at the why it's a fancy group. Take the real line. The God-given measure on the real line is Lebesgue measure, which is infinite. You can say, I want to take something absolutely continuous and finite, say something like the Gaussian, and then work with that or whatever. But for many things, having translation invariance is something that you don't want to lose that convenience. And when the underlying space is non-compact, it's like the real line, you have to deal with these infinite measures. So if you want to study L infinity of the real line with Lebesgue measure, then for the real line, the rational measure is Lebesgue. So it is silly to say I will only look at finite measures, because only those will give you linear functions on odd of L infinity by integration. Okay, so let me just list some properties of this thing. One, I'll drop the phi later. If there are more than one coming, then we'll write the subscript. I'll just write D and. So first, the D is a why does it get used to these words? Hereditary positive cone. M plus. Why should I say M plus? Hereditary positive cone. See, what does that mean? Hereditary means if I have x at D, A and M plus, A less than equal to x implies A and D. This property is inherited by anything which is smaller. The property of being in D is a hereditary one. And positive, you know what a positive cone is. It means exactly that if you multiply by a positive number, any element D multiplied by a positive element is again there. If you take any two elements in D, their sum is again in D. That is if x and y are in D and if alpha is a scalar, alpha x plus y, if alpha is a positive scalar, then alpha x plus y is in D. That is clear because we've divided a phi that it satisfies that kind of linearity, positive linearity. So it's only this hereditary thing that we have to see. Oh, okay, well, that is clear, right? Phi is positive. It's a positive. This means what? This means that x equals some A plus B. Where A and B are positive. That means phi x must be phi A plus phi B. And if phi x is finite, then certainly both phi A and phi B must be finite. Okay, this is simple enough. This is a little more interesting. N is in M. It is all those x and m so that x star x is in D. N is not in M plus. It is those things for which x star x has a finite phi value. Sorry. Hello. speaking. I'm in the middle of a class now. Can I call you back? That'll be good. After 7 will be good. Okay. Yeah. Thank you. Okay. Okay, so this requires left ideal means that means you must show that n is first it will be a linear subspace. And then it must be invariant under left multiplication by elements of M. So it is clear that it is closed under multiplication by constants. You multiply an x in n by any scalar alpha, then alpha x is also going to be in n. And what about y?
Phi of x square, phi is arithmetic.
That's right. But if you take
If x belongs to n phi and y belongs to n phi, phi of x star x plus phi of y star y, both is less than infinity.
y,
Because phi of x star x is less than infinity and phi of y star y is also less than 4 times.
but y is phi of x star y finite.
You have to prove that
Phi of x star y plus y star x. Why is that finite? So here is a little trick. If you take x plus y star x plus y, there will be the nuisance of a cross term. X star x plus y star y plus those other things. X star y plus y star x. But on the other hand, let me observe that this is smaller than this is the kind of trick that we saw in polarization ironically. If you take x minus y star x minus y, the two cross terms will come with a minus sign. So if you add these two things, the cross terms will disappear. So all you'll get will be twice x star x plus y star y. And so it follows that phi of this will be finite. Okay? This implies that n plus n contained in n. And what about left ideal? If you take ax, if x in n and a in m, you want to look at AX and see if that is in N. AX star AX is what? X star AX. But see, A star A is smaller than or equal to norm A squared. And the operation of Z going to X star ZX is positive. It preserves positivity. And Z going to X star Z, ZX is positive. It's auto-preserving. And so this will be less than or equal to norm A squared times X star X. Okay. Then the third condition I want to make is that M is a star subalgebra of M. It is not unital or anything. I'm just saying it is closed under star and products. It is clear that M is closed under taking star. And why it is an algebra? Because N is a left ideal. See, M is closed under addition, so it's enough to take just one term. If you take y star x times y1 star x1 times y2 star x2, you can write as somebody star times x2. I didn't say that right. If you take y1 star x1, y2 star x2, see here all the x and y are in N. In M by definition, suppose you take xj, yj in N. Then M is a combination of things like y star x. But if you take this product, then so what is silly? See, we proved that N is a left ideal. So N star will be a right ideal. Then we will take adjoints. So y star x will be an N star. And similarly, y2 star x2 will be in n because x2 is in n. N is the left idea. Actually, see, if you take n star n, that will be contained in n star intersection n. Because n star is the right ideal and n is the left ideal. So if you multiply anything in n on the left by anything, you will be in n. If you multiply anything in n star by anything on the right, you will be in n star. So this is going to be contained in n star intersect n. Here, because this is right ideal, and this is left ideal. So, and each of these products is in, I should not say anything more. See, this whole thing we know is going to be an n star. This whole thing we know is going to be an n. And hence this product will be an n star n. And so the sum of such things will be indeed a star subalgebra. This is a slightly more interesting assertion. Assertion that this D is exactly M plus. By which I mean, of course, M intersect M plus. Go back to think of in terms of L2 and L1 and so on, it will be not so surprising. This is like L2 and this is by Cauchy-Schwarz, this is L1. And you're saying that this and this are the same. This is exactly the positive L1 functions. This is all of L1. So we just need to give a non-commutative argument to say the same thing holds in this case. Okay, maybe this is a good time to stop and or let me see if we can hurry through this proof. struggled little proof. So I want to say that in fact every element of M, they're just like the usual kind of I should go back to the statement. In fact, I want to say every element of A and D implies there exists Zi in M plus so that A equals summation I equals 1 to 4. That is that everything in D can be written as sum of 4 elements of M plus. This is really like saying that anything that's a complex thing can be written as sum of 4 not quite, but okay, let me do this proof next time.